Hello and welcome to this ACE Physics review session. Question 1 reads, complete table 1.1 by stating whether each of the quantities is a vector or a scalar. Let's use this as an opportunity to review. There you can kind of see what we got into during some astrobiology, considering the best definition of life and the 11 organ systems that keep human beings alive. We were considering the maximum entropy production principle earlier. We'll save that for another day. On to the fun stuff, vectors and scalars, right? If that piqued your interest, just sign up for astronomy next year. Lots of good physics there too. So a vector, remember, is a quantity that has both magnitude and direction, while a scalar is magnitude only. There are no directions associated with scalar quantities. Acceleration, that's a vector. Power, that's a scalar. And work, that's a scalar. So acceleration is the rate of change of velocity. So velocity is a vector. So velocity over time, acceleration, both of those are vectors right there. Power, you may recall, is the rate at which work is done. So work over time. Work is energy, like the rate that one form of energy is converted to another way to think about it. You could also remember that work is force times displacement, and that displacement over time is this velocity. So we got force times velocity. So even though both force and velocity are vectors, you can multiply two vectors and get a scalar called a scalar product or a dot product. And work is another example of that, where work, like I mentioned, is force times displacement, but it's the dot product of force and displacement, meaning only the component of force that acts in the direction of displacement contributes to work. And so that's the full form of the equation for work. Work and power, both scalars, acceleration, a vector. You should know for all of the quantities we've studied throughout the year, whether they are vector and scalar, and you should really be able to define them precisely, because you may have questions that will say things like state what is meant by, or define work, something like that. Question goes on to read, the variation with time t of the velocity v of an object is shown in figure 1.1. And so it looks like, let's just sort of inspect this. This thing is starting at a non-zero velocity. It's going kind of pretty slow here, right? Like it goes from 0 to 1.5 meters per second. So it's kind of like just less than 0.75, and it climbs up to like in between here. And then it stays that fast for a bit, and then it slows down to a stop, right? 0 meters per second means stop. So it's slowing down to a stop. All right. Speeds up, stays at a top speed, and then slows down. All right. It says determine the acceleration of the object from time t equals 0 to t equals 4. And so that's this, sort of first part of it. Acceleration, when you're looking at a velocity time graph, you can kind of use the units as a clue. The rise is in meters per second. The run is in seconds. So if I took the slope of this, it would be meters per second, or meters per second squared, which indeed are the units of acceleration. And so the gradient of a velocity time graph is acceleration. And what we need to do here is just take the slope of that part of the graph. So let's try to read the scale here. If this is 0.5 and that's 0.75, and there's 5 lines between, and each one's going up by what? 0.05 is like 0.55, 0.6, 0.65, 0.7. So that point right there is 0.7. And then it goes up to this point here, which is 4 seconds. And so that's the x coordinate, and that corresponds to a velocity of 1.3, 1.35, 1.4, right? 1.4. That, what did I say? 3, 3, 5, 4. 1.4. Math people know that y2 minus y1 over x2 minus x1 equals slope. That's the same thing as saying the rise over the run is the slope. When you subtract 1.4 and 0.7, it's like counting the rise, right? It's like 1.4 minus 0.7. It's like the difference between this and this, I'm like counting the rise. And then the difference between 4 and 0, it's like I'm running from 0 over to 4, right? Kind of shows you why this works here. 1.4 minus 0.7 is 0.7. 4 minus 0 is 4. 0.7 divided by 4 0.175 meters per second squared. I might round that to 0.18 meters per second squared. So that's what you should get for determining the acceleration of a velocity time graph. I know it's tough to work sort of off of a screen in front of you or off of like a projector. It's like you want to see that graph in front of you, right? So I'll give you some time to, if you wanted to like, do a rough sketch of that figure, or maybe the important note to write down is gradient of velocity time gives acceleration. I can imagine they're going to ask us, I can anticipate a calculation of the distance traveled, right? Because that's the other thing you can do is sort of take the area underneath that curve. But this is why we, sort of practice this a lot with our lab work, finding the slope of the best fit line. It's really what all science is about, trying to look for relationships, trying to sort of see that there's trends between sort of independent variables that we can manipulate and dependent variables that we can measure. Oh, look, because I changed this other thing changed as a result. It depends on this change. To show that how those things are related is really what science is all about. Question goes on to read, determine the distance moved by the object during that same time. From t equals 0 to t equals 4, what's the distance? All right, so let's go back up to our graph here. And so, raise your hand if you need any of this for a moment or two longer. Not you, YouTube, you just pause it and rewind it a little bit. I'm talking to the present in-person and e-learning students that are here live. Anybody? E-learners? Good to go on that? All right, check the video later if you need. Now we've got the area underneath this curve, and so only sort of this area here. We can look up the area of a trapezoid. I think it's like base 1 plus base 2 times the height times a half. Okay. We could look that up. Anyway, we'll just break it down like this. Triangles and rectangles, right? So we want the area of each of these. Now remember that this is actually where we derived this equation of motion. So you can kind of remember, like, I can solve for the displacement. It's the initial velocity times the time plus 1/2 the acceleration times the time squared. And since we've already solved for the acceleration, we know this is 0.175. Plug that in. We know this is happening over 4 seconds. We know the initial velocity was 0.7 and the time still 4 seconds. So that working there will solve it. And it agrees with just sort of saying, okay, here's my initial velocity, length times width, right? Rectangle, find the area of a rectangle. The width is 4, the length is 0.7, that's that term there. This area represents, this term here. There's no acceleration, right? So we're not accounting for the speeding up. It's like something going this fast is like distance equals rate times time. This is like the definition of velocity. Okay, so the distance we'll cover is the velocity times the time. How fast we're going times how long we're going that fast will be how far we go. Now this is harder to sort of realize why sort of this term sort of works here. But if you recall how we counted up from v to u, so if we say like the initial velocity down here is u, the final velocity up here is v, this is v minus u over t is acceleration, right? We said that the gradient of this, the rise over the run, so the rise is the difference in the velocities, the run is the difference in the time, but time not is 0, so we just sort of eliminate that. And so we rewrite this as v minus u, which is the rise, right? The difference between v and u is equal to at. So this sort of, the base of this triangle, if you will, is at. And remember that this is t, right? From 0 to 4, that's t, the time. So if we take the area of a triangle and just realize it's 1/2 base times height, that's where we get the 1/2 at squared. The area of this is 1/2 at squared. It's not immediately obvious to see why the, like where that at comes from, right? But if you look at the definition of acceleration, then it is pretty clear. And again, since we've already calculated acceleration, we could sort of solve it that way. 1/2 base times height. So again, by just sort of counting out the height, that's v minus u, you're sort of solving for what at is without ever really knowing a. In other words, we didn't have to know what the acceleration is. We could have simply said, well, what's 1/2 base times height, and just use our knowledge of geometry to solve it. We'd say the base of this thing is 4 seconds, the height of it is, and then there we would be calculating the difference v minus u, right? Because the height goes from, what was this, 1.4, right? And we went 1.4 minus 0.7. It was the numerator in our slope calculation. You know, that is the height, right? And it just happens to be equal to at. So sort of folded within that is the acceleration that we calculated previously. So, you know, equal ways of thinking about it. And hopefully, as you work more with the ideas, you begin to realize how they connect pretty nicely. You know, they're sort of one and the same. All right, so all we got to do now is some numbers. 0.7 times 4. I like to solve it sort of like this. So I say, okay, if I didn't accelerate, if I just go 0.7 for 4 seconds, I would have went 2.8 meters, right? And the units here work too. So meters per second of velocity times seconds of time give me meters. I can only add meters to meters. You can only add quantities with the same units. So, I mean, I guess you don't have to. Like I could say, I'm 6 feet 6 inches tall, right? Or I could just say, oh, I'm 6.5 feet tall, right? It's the same thing, but these are sort of mixing units together. And, you know, there's an example. I guess we do sort of do that in practice. But usually it's like, we're not going to add meters to centimeters. You know, we're just going to sort of combine them with the same unit. So always check your units and do conversion. That's almost 2 meters tall, you guys. It's like 198 centimeters. So close. All right, so 4 squared is 16 times 0.175 times half. I got 1.4 meters for this. Now this is to scale. So you kind of look at it and you say, yeah, the area of this one, in fact, look, it's twice as much as this one, because if we just sort of box this off over here, right? Because the height 0 to 0.7 is the same as this to this, right? We've doubled our speed from here to here effectively, right? So the height of this is the same as the height of this. It's like, oh yeah, this triangle, 1/2 base times height, that's just half of a length times width, right? So you go length times width, half it. So there's your formula for a triangle for good measure. 1.4 plus 2.8, 4.2 meters. So all that gives us 4.2 meters. That's a nice little kinematics question, looking at graphical analysis with velocity time graphs.